I'm fantastic today. That's what I'm doing. Put this here. How we doing, Khadija? Let's change this over. There I am. Hey, there we go. Hello, hello, hello. How we doing today? How we doing on this fine Thursday? I hope we're doing absolutely fantastic. Fantastic. Doing okay? Alright. Well, okay is better than not okay. I'm gonna take that. I'm gonna take that. Very good, very good. Ready for, yeah, look. If you can believe it, we're down to our last two sections. Down to our last two sections. If you can believe it. We have made it here toward the very end. We're actually almost there. It's a miracle, I know. What are we gonna do next week? Yeah. So for the classes that would be left over after doing all the sections, once we're done, we'll be going over any review questions that you may have. So you can ask me any questions that you have and say, hey, can hey, Professor Chips, can you go over this question? And be like, okay, cool, I can go over that question. So got here until the here until the end of the semester for you to ask me any and all questions that you may have, and then and you can get those stuff clarified and get it, hopefully get your homework or tests, you get that stuff knocked out and get your good grades. That's important. Yes. So that is the plan. That is the plan. I wouldn't leave you guys hanging just because we don't technically have any new material. No, I'm still gonna be here. I'm still gonna help you out. That's just how it rolls in this class. That's how it rolls all the time, but you get the idea. Yeah, I'm going back taking all the notes again. I'm gonna properly sit down and binge the rest of the homework. Oh, well, if you're gonna binge it like you do Netflix, then yes, please do. I would like you to do that very much, Khadija. Let's read those. Actually, it's down. Wish was easy Netflix. Joseph feels the same way, apparently. Joseph's like, hey, I wish it was as easy as Netflix. I know, I know. I know, listening to me for 2 hours is not as easy as watching some Netflix specials, I understand. I understand how brutal my voice may sound after hours and hours and hours of me explaining stuff. Listening to my own voice on my replays, I barely watch replays of myself. I'm like, I don't want to listen to myself. I already listen to myself all the time anyway. Hey, Nicholas! Good morning / afternoon to you. Hopefully you're doing fantastic today. Where are we here? Go. Doing good? I'm doing absolutely fantastic. Absolutely fantastic. As I was saying earlier, we've got a couple sections left, and then we're done with any new materials, so we're getting close to being finished. That's what we're kind of after here, at the very least. So, at least I hope so? Question mark. Turn that up. There we go. I got 3.1k points. There you go. Khadija counting up the amount of channel points she's collecting. Channel point collector. Racking up for the super hydrate. Okay, that's fair. The super hydration. I see how it is. Drink the rest hydrate. God. Jess, hello. Good morning / afternoon to you. How we doing? How are we doing? What is everybody's plan for the weekend? Just to knock out homework and stuff? I don't know. I don't know if your plan for the weekend is to knock out homework and get it done. Hopefully get things going. Get it rolling. I hope so. No question mark, question mark, question mark. Got a couple weeks to go, so. I can't believe there's only this much time left. So fast. So fast when things go by really, really quick. We're gonna wait. I know I got a little bit late here online, so we're gonna wait a couple minutes here for a few more people to join us. Then we'll go ahead and get going here with some material. Material, yes. I'm ready to destroy all of you. No plans for you. Hopefully finish today's homework and today and have the weekend free. Oh, very nice. Nice free weekend can't hurt for anyone. I agree. This week has been actually pretty fruitful for me. I ain't gonna lie. Yesterday was actually a pretty decent day. So I will not complain about yesterday. Yesterday went to the dentist, got that stuff done. Made like $700 in a day. That was pretty decent. And yeah, I can't complain. There you go. You get more than 3 hours? Yes, I did. I was knocked the heck out last night. I can't really argue. So $700 on trade. I can't really argue with that. You make a good trade, and you're like, oh, you make $700 off of a stock option trade. I'm like, oh, that's so great. I love you. And I bought another position yesterday after that trade, and then I made another 150. I just sold that off today. So, there you go. That's how it rolls. That's how it rolls. Let's see, I'm monitoring a stock right now. So, very popular one. This. Where are we at? Oh, good timing too. That price is decent. Yeah, can't really argue with some free money, free money to collect what you lost. $700 easy. Been going crazy about AMC for the last little while. Yeah, so what I did is I just traded some options in Apple, and I won pretty big on Apple. So I was like, oh, here's $600 for this trade on Apple. Great. I guessed correctly. Ain't gonna complain. Re-upped an Apple again, made another 150. I'm like, yeah, I could roll it. Yeah, I know we could talk about meme stocks and stuff like that, but I don't know. There's not talk about AMC and GameStop and stuff like that. Like my first ever tweet was about GameStop. It was like at $2 at the time or something like that. Now GameStop is like what, $200 or something. So yeah, it's kind of crazy. You think about it. But they're not as many opportunities to. There's not as many opportunities to get in on really ridiculous multipliers outside of crypto. Reddit make that skyrocket. That's true. Yeah, Reddit made that skyrocket for sure. Saved the whole company too. No, without question. That GameStop was gonna go under without Reddit making it work as crypto was crypto is still a definite crazy time. Crypto is still crazy. It's still crazy. So right now there's not as many regulations on crypto right now. So you have governments trying to rein it in terms of regulations and whatnot. So you see a little bit pushback from other countries' governments, but it's a there's still money to be made regardless in Bitcoin and whatnot. It's not going to be as crazy as it was right now, because obviously, it's got. I guess for some governments it's got out of control, so you had to be a little bit careful. Ema, hello, how you doing? Hopefully you're doing fantastic. What governments are necessarily scared about is like destabilization of the currency by switching over to crypto compared to their own fiat currency. So then they get worried that they don't have control over the actual money supply. Okay, yeah, I will. I answered that question earlier, but I will certainly say that again once I do my intros here. You better keep doing the streams. Am I a fan of cryptos? Not really. I'm invested into one crypto, but I'm like very cautious even about that. So, I mean, it wouldn't be. Nah, don't worry about it, man. It's not a big deal, my dear. Not a big deal at all. You're just fine. You came just on time. I haven't even started yet. All right, let's do some intros here. We'll have more people join us, I'm sure. And along the way, let's do this. All right, let's get it done. Okay, let's get started today. Welcome back to Thursday, end of the week time today. All right, so to answer your question there, E-Man, my dear, we have, what are we going to be doing after we do these next couple sections? Because, yes, we have 2 more sections left to do here. That is here in Chapter 8, okay? That'll be specifically sections 8.1 and 8.5, okay? So just those 2 sections from Chapter 8, 8.1 and 8.5. Now, what we're doing after that is, yes, just to be sure, I am still going to be continuing the streams, regardless of the fact if we have new material or not. What I am going to be doing here is what I usually do, and that is, if you have questions over any homework problems or the like, you guys feel free to ask me. That is what we're going to be doing here for the next, week and a half, 2 weeks here. If we finish off Chapter 8 here today, then it'll be the next 2 weeks, obviously, or just a week and 3 days. Regardless, yeah, up until the very end, you guys want to ask me questions. That's what these streams will be here for. They will be here to say, hey, I want you to answer, such and such question from such and such section. I'd be like, cool, let's do it together, and I'll show you how to do it. So that is the plan here, and I have no problems taking 2 hours answering all your homework questions to clarify anything. As what we're here to learn, so that is what it is. So we can finish the homework and take the final after Chapter 8 is finished, and would be done with class. That is correct. Yes, that is correct, Nicholas. You're spot on. You could finish the homework, and if you're satisfied with your homework score and you're satisfied with your test scores, you take the final, and you would be technically done with the class. Yes, absolutely, 100%. Again, I told you before, Nicholas, you take it at your own pace. So, I like I said before, I'm not forcing it on you guys. Again, I told you before, it's all due on the 29th. If you want to wait to the last minute, that's a you problem. But if you want to do it, next week and get it done, and you'll be done with the course. That's perfectly fine. And then you come on the live streams, just have a nice fun time. I got no problem with that whatsoever. So I mean, like I said, this class has always been made for all of you. All right. These live streams have been made for all of you. So that's what I'm here to do. That's what I'm here for. Whether it be one person or whether it be 100 people, I'll still be here, hopefully helping you. That's what I'm here. What I'm here to do. So. So technically, if you're ahead of game, class could be over this weekend. Truth. Or unless you're me, in which case you're here till the 29th. Yes. Though I have a feeling you'll be sleeping for the next 2 weeks and then wake up on the 29th and then try and do everything at the very end, right? Is that what's gonna happen, Khadija? Am I assuming that that's no? Emphatically no. How can I have such little trust in you? I have little trust in myself. No, I know you'll do fine. I'm just teasing you. I know you do fine. I know you have been putting in the effort here to come to every class. So I haven't I haven't been trust me. I've been noticing. I've been so scared to take the test. I have a huge fear of failure. It's not even funny. Well, that's why I put the practice tests up there, E-Man. Practice test is to make sure that you understand all the questions that will be on the test. Because the practice tests are exactly the questions that are going to be on the test, just different numbers. So, and you get bonus points for trying the practice test, as I've said before, E-Man. So, the bonus points have not been added to the percentage that shows on my math lab. Yeah, that's going to be done on D2L. I obviously have a lot of stuff to enter in on D2L, but, that's be done after the 29th, so that's a me problem. Yeah, trust me, the practice tests will help a lot, and they will help ease your anxiety, okay? But, E-Man, you gotta go try the practice test first, okay? Being afraid, I understand failure's not the greatest thing in the whole wide world, but, I guess you're talking to a guy who's failed before plenty of times. So, yeah, you know what? I will say this. I put the practice test so it avoids that fact, but you gotta have confidence in yourself just to go out and do it. I give you even multiple tries on the test. It's not just one try. You get like 5 tries to get the best score possible. Okay? So it's not like even that. You get infinite tries on the practice exam. Once you go ahead and take the test, you even get 5 tries on that. So, but you gotta get that stuff knocked out early here because again, you got 2 weeks to go. Make sure you take your time and get those grades that you want. Okay. I'm not a big fan of tests either, and the practice tests help. Yeah, that's exactly what it's supposed to do. Yeah, look, I've been on the nasty end of failure before. Okay. All right. I've been on the funny end of failure before, and I've been on the nasty end of failure before. So, I'm just gonna say, I've been there, I've done that. It's not a great feeling. In some cases, it was a nice feeling. In one case, it was a nice feeling when I failed my computer science final. But, yeah, that was, best class I ever failed was computer science, and then I went and got a degree in it anyway. That was at U of I, though. Computer science, I ain't gonna lie. Computer science, I ain't gonna lie. There's like 500 people in the room taking that test, and I didn't know what I was doing. I think I wrote down the answer to one problem, handed it in front of 500 people, walked out of the room, and just put my hands up and said, "I failed. It feels so great." Let's just say that that contributed to my worst semester ever. So, yeah. That was one of the classes that contributed to my worst semester ever. So, let's just say, yeah, got my ass handed to me, and rightfully so. So that's okay though. And sometimes when you fail, you learn from that failure and decide to try something different. All right. All right. Well, we got to move on here with the material at the very least. Let's go ahead and see if we can get the last couple sections knocked out. All right. So let's take a gander and let's see what happens. Oh boy. All right. All right. So today we are going to do 8-1 and 8-5. Let's go to the big board. Let's see what we're. Okay. So here we have section 8-1 and 8-5. We're going to be talking about sequences. We're also going to be talking factorials, the summation notation, and the binomial coefficient. Okay, so that's going to be what we're going to be doing in these two sections here. We're going to need to go over each part here, and we'll go over, naturally, some examples, of course, just as usual. All right. Go to a single page here. Okay. Go. Okay, so let's look at question number 1 here. Question 1 says, what is a sequence? Okay, so a sequence is a series of numbers or terms or whatever, objects or something like that follow a distinct pattern that can be defined. Typically, for a finite sequence, this can be listed as elements of A1, A2, all the way up to AN. So for example here, you could have a sequence, the very basic sequence of numbers like 1, 2, 3, 4, 5, 6, 7, 8. That would be a finite sequence because you have 8 particular and unique numbers that follow one at a time, obviously. All right. Or you can even have infinite series of numbers, so such as even numbers. So you could have 2, 4, 6, 8, and then go on infinitely because there's an infinite amount of, say, positive numbers that you're going up by 2 every single time. All right, so what we're going to be doing here is looking at these sequences and being able to solve for these particular sequences, or at least write the first few terms of a particular sequence based on what is given. So what exactly does that mean? You know, I speak words, but let's put into action. All right. So what that exactly means here in this case is, let's do a quick example. That's okay, Lysidena. I'm just glad you could make it. I'm sorry it's been a rough week, though. I do apologize. I hope that the end of this week, though, will be significantly better. So, yeah. It's no fun having a rough week, right? But you know what? There's always a silver lining on the horizon. Hopefully, at least it's been productive, and hopefully you can get through it. Whatever's happening, hopefully you can get through it. Hopefully we can end the week on a positive note, Lysidena. Okay. All right. So let's go over this here. Let's go. Understandable. Understandable. I understand that that's a rather difficult situation going on out there. All right. All right. So let's do let's go to an is equal to 3n over n plus 5. All right. So what we want to do is, in this case, we want to find the first 4 terms in the sequence. Now, this is basically the generic pattern of each term in the sequence. Now, you notice that we have n here. N here is like an, 3n over n plus 5. So here we have, let's start off with a1. So that means that whatever this number is, this little subscript for a, that's the number that we're going to put in for n in this particular formula. So all we're going to do is we're going to have 3 times 1 over 1 plus 5. So here we get, again, you simplify this down, you get 3 over 6. sorry. It's going to bother me. Equals a half. Okay, and that's all we got to do for that. Simple enough. Let's try the next one. Let's try A2. I needed to zoom in there. Let's try A2. A2, we're just going to plug in 2, in for n. So we get 2 plus 3, so that's equal to 6 over 5. Good. Rinse and repeat here with 3. We get 3 times 3 over 3 plus 3. We get 9 over 6, which can be reduced to 3 halves. And then since we need the first 4 terms, just plug in 4. A4 is equal to 3 times 4 over 4 plus 3. So we get 12 over 7. So our first 4 terms are 1/2, 6 over 5, 3 over 2, and 12 over 7. Okay. And that's it. Those are your answers there. The 3 isn't the 5. Yeah, this is a 3. I want the first 3 terms there. Wait, what did I do? Oh. I guess I did do that. Yeah. I guess I went with 3 for some reason. Maybe talking about failing computer science has made me fail to see that this should have been 5. Let's try it again. Nobody saw anything. They didn't see nothing. None of you saw anything. You all bore witness to absolutely nothing. I will neither confirm nor deny my stupidity. Okay? Exactly. Okay? I agree with all of that. Oh man, that sucks. I hate when I do that. So annoying on my part. Probably annoys you too. So, okay, good. I have no idea what I'm talking about either. So, we get 6 over 7, 9 over 8, 12 over 9. Oh, 12 over 9 actually reduces. That's 4 over 3. No clue whatsoever. Even like, you know, I had no clue what he was talking about from the first day of class. I'd be like, yeah, I kind of don't disagree with that statement. As soon as he started talking about numbers, I just was lost. It was over, right? He walked he came into this Twitch channel. First of all, you first looked like, I gotta go to Twitch for class? Okay. You walk into the channel. Wait, what? I'm done. I'm just done. I come to this gaming platform and I have to talk about mathematics. Like, what's going on here? What's the world coming to? This is not what I signed up for. Never even heard of Twitch. There you go. Something seems fishy. Who's this guy and where did he come up with this crap? It's all a simulation. How did you know? This Dr. Pepper with 0 sugar. It's all simulated 0 sugar. Okay. In fact, the sugar is so simulated. The sugar is so simulated that it doesn't even exist according to the bottle. That is, it's absolutely unbelievable. I'm not gonna lie. I'm thinking this is an ECC class, but I have 13-year-olds from the UK chiming in. Hey, look, I got people from the UK chiming in all the time. No, they're absolutely fantastic, though. Let me be honest with you. People in the UK, they chime in because the only reason why I get a lot of people from the UK is because of my um because because of hashtag United. So 'cause I'm big in that I'm really big in that community because I love hashtag United. So I will shill for that club to the end of time. I think 100%. Oh man, super fun loving a football team across the pond. Can't really argue. All right, I know I gifted him a lot of subs. Um, yeah, I gifted him a ton of subs, like 1,000 subs. So I want to support that team. So, all right. Joseph's like, hydrate, okay. Hydrate. All right. So that first example there, thank you for the hydration, Joseph. So that first one there was for sequences. All right. So that's the first example we did here. All right. Let's do the next one, which is the next question here, number 2. Number 2, how do we solve recursive formulas for sequences? Now, if you've done computer science, recursive formulas here are one of the mainstays, staples of actually programming functions in computer sciences. But what does recursion mean? Recursion, or recursive, means you use the previous terms in the sequence to find the next term in the sequence, so using the formula that is given. So you can't do a recursive formula without having a base condition and a base formula of which to work off of. Again, very popular in computer science to use recursion quite often. Um, so let's go ahead and take a look at an example, and we'll see exactly how this works. So let's say we're given here. We have to be given a condition. So let's say a1 is equal to 12, and we're given the fact that an here is equal to an minus 1. Let's go with actually I'll go with the 3 in the front. 3an minus 1 minus 4. Okay, so I have 3 times an minus 1 minus 4 is what we have here for our formula. Now, the important part here I want to point out is we want to find the next 4 terms in the sequence. Okay, so the way you want to do this is very simple. We're given already a precondition here. So let's say I'm trying to find out what a2 is. Now n here is equal to 2, so we have 3 times a to the 2, a2 minus 1 minus 4. Now 2 minus 1 here is going to be a1. All right. Now we already know what a1 is. a1 here, this is where the recursion comes in. We have to use the knowledge from the previous term. We're just going to go ahead and plug that in. So we get 3 times 12 minus 4. That's 36 minus 4. That's 32. Okay? So that's a2. And now we want to go ahead and rinse and repeat this process here with the next 3 terms. So then a3 would be, again, 3 times a3 minus 1 minus 4. So we get a3 is equal to 3a2. Uh-oh. Trying to do 2 steps at once. So I get 3a2 minus 4 And again, we use this previous definition of A2, which is 32. So we get 3 times 32 minus 4. And so if you go ahead and do this here, you get 96 minus 4. That's 92. So that's A3. And then again, you can repeat this process for the last two terms. You can pretty much get it here. I'll have you guys confirm these last two terms. What do I get for the next one here? It's 276 minus 4, 272. What do I get for the last term here? A5. A5, 272. What is that? 810, 816, 816, 812. Okay. Alright, good stuff. Alright. Alright, good beans. Alright, so that's our answers here that we get here for the next four terms in a recursive sequence. Okay, any questions about that? Hopefully that wasn't too bad. Hopefully that was pretty easy. Question mark, question mark, question mark. Any allergies? Alright. Easy, Tom, easy. Alright, next. Alrighty. Alright, next. Let's go over the next part here, which is talking about factorial notation. Alright. So, let's talk about how we can do factorial notation here. Now, what is factorial notation? As you can see here on the screen, factorial notation uses the exclamation point here in order to showcase factorial notation. Now, n here is going to be n factorial. N has to be a regular positive integer, so you can't have negative numbers or anything like that. Just nice regular whole positive numbers. Now, what's this going to equal to? It's n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. So I put an example down here for 5 factorial. 5 factorial here would be 5 times 4 times 3 times 2 times 1, which would equal 120. Also, as a good note here, because this is used quite often, 0 factorial actually has a definition as well, and that 0 factorial here is going to equal 1. So one of the properties here for factorials that we will use a little bit. Okay. So if I were to go ahead and figure out here how factorials work, again, you could multiply it out. Here you have, let's say you have 18 factorial. Let's do a couple quick examples here. Let's say I had 18 factorial divided by 16 factorial. All right. So, do I want to become famous? Why, you, my friend, are more famous than I am because you're on my short list of bands. All right, so how would I go ahead and do this? Go ahead and do this problem here. So the way I would want to go ahead and do this problem here is that we have 18 times 17 times 16 times 15 all the way down to 1. However, one of the things about factorials is that you're just going all the way down the line. So, meaning to say, if I multiplied by 16, again, I do 16, 15, 14, 13 all the way down to 1. Here I have 16, 15, 14, 13 all the way down to 1. But technically, 18 factorial divided by 16 factorial would be 18 times 17 times 16 factorial, because you're going 16 all the way down to 1, and 16 factorial is also the same exact thing. So in effect, you look at this and you're like, wow, that looks very, very intimidating because you have really super large numbers. But in reality, you actually have, it's actually easier than you think. You can actually do it by hand, and you can say, well, you can just cancel out the 16s. And that just leaves you with 18 times 17 at the end of the day. Just going to get, what is that going to get? 180, that 126, so 306. Okay. All right, there we go. Good stuff. All right. All right, good beans. Now, one thing that you can do on the calculator, and we are going to look at the calculator here briefly. It's actually for certain things that we'll be looking at here for these two sections, using the calculator in some capacity. So let me bring up the calculator here. See how this works. Yeah. All right, so you can do factorials here on your calculator. All right, thank you. I wanted like half a screen. All right, so if you want to do factorials here, let's say you want to do 18 factorial divided by 16 factorial, you can do 18, and to get this exclamation point to show up on your calculator, you can go ahead and hit the math key on your calculator, and you can scroll over to the PROB submenu here. And if you notice here, if you take a look at number 4 is that X, that's very same exclamation point to represent factorial. Okay, so we want to go ahead and hit enter here on that. And we divide that by, of course, in this case here, 16 factorial. That's 16. Hit the math key, PROB, and go over to number 4 again. And then, as you can see here, we get 306, just as predicted. Any questions about that so far? I'm going to do one more example here. So, okay. So the other example I kind of want to show off here. No, all right. We have one more example I want to do, because this will be relevant for what we're doing later. So let's say I had an example like this, 20 factorial divided by 3 factorial, 17 factorial. Again, you can take this 20 times 19 times 18 times 17 factorial. And again, we have 3 factorial, which is 3 times 2 times 1 times 17 factorial. Again, the bigger numbers here will just cancel out. Fairly convenient. You can cancel some more stuff out here. 3 and 18 go in together 6 times. 2 goes into 6 again. We have 3 here. Okay. We actually have 20 times 19 times 3. And so, what's that going to be? 57. So, 57, 1,000, 1,140. Okay. All right, so 1,140 is going to be our answer. Again, if you want to check that on the calculator here, you hit you hit 20, go to the PROB, go to factorial. Now, since you have 2 things in your denominator, you just go ahead and section that off. Division would be nice. Go ahead and section it off with some parentheses. So 3 factorial times 17 factorial. At here. And a number 4. And here, indeed, we get 1,140. All right, bada bing, bada boom. Yeah. All right. Any questions about that? Again, you could confirm that your stuff here using the calculator. I just did the calculations in my head, so calculations of numbers in your head, man. All right, good stuff. Easy peasy lemon squeezy. All right, let's move forward then. Let's take a look here at the next part in section 8.1, which is the next question, which is number 4. Number 4 says, what is summation notation? All right, so summation notation is the next thing we'll talk about here. This section has a smattering of a lot of different things, so hence why we're just kind of going from one thing to the next. So summation notation basically is you take every element in a sequence and you just add them together. But they're given in terms of notation here by this huge sigma guy. Now, if you take a look at this carefully, I'm going to put this front and center here. If you take a look at this carefully, here it talks about an index here. It just goes from 1 to n, however many numbers that we have to add together of this AI. Again, this AI here will be the sequence, okay, or the definition of the sequence, and then we have to figure out what those numbers are and then add them together appropriately depending on how many, what we go from 1 to however much that we have to go to. Now, the important part here is let's look at an example. Let's look at actually a couple of examples for sure, because there are two different ways to kind of approach this. So what do I go with first? All right, so we're going to go over a couple of simple ones here. So I over 1 to 4 of n. Okay, so let's say you run into this situation. Now, I want to highlight how summation works here. If you're given this situation here, you have the summation from I equal 1 to 4 of a number here of 10. All right, so if you're given 10 here, all you have to do here is notice you're going 4 times. You're just adding something 4 times. So in this case, what are you adding? You're adding 10 by itself 4 times. So you have 10, which is the first one. That's the first. Plus 10, which is the second term in the sequence. Plus 10, which is the third term in the sequence. Plus another 10, which is going to be the fourth term, because that's, again, what we're going to. So 1, 2, 3, 4. Starting from 1, going up to 4. So if we add 10 4 times, then obviously we get 40 here. And that's going to be our final answer for that problem. Okay, so it looks hard here. In reality, not as bad as it may seem. Let's do another, like this version of math. Good. Well, we're going to do another nice example here. Let's go 1 to 5. Okay. Let's go 5i. So sometimes they'll give you a definition here in terms of I. Okay. So maybe they give you 5i here. So all you have to do is if you just go each term down, you start off with 1. So you go 5 times 1. That's the first term in the sequence. And the second term here, you add that to 5 times 2, because I would now be 2 here. That would be the second term in the sequence. And you go all the way down here until you go to 5. Once you hit 5, that's going to be, oops. So this is where you would stop, 5 times 5. Okay? And so then you just figure out what each of these terms are. Again, third, fourth, fifth. How do you know to stop at 5? Because it tells you to stop at 5. You go from 1 to 5. So you have 5 plus 10 plus 15 plus 20 plus 25. All right, so that's 50, 70, 75. All right. All right, so that wasn't so hard. Hopefully, that's pretty easy. All right, so that's how you approach at least those two quick ones there. It can be a little bit more complicated. Again, just be a little bit careful about where you're starting and where you're stopping. So what's another one here? Another one here would be, I'm just going to borrow one here that's a little tougher. If I equals 1, why do you move up to 5? Again, that's where you're starting from, Brian. So you go from the first term to the fifth term. That's what these two guys represent. So you're plugging in 1. This is where I would be, right? You have 5 times I. Is that correct, Brian? So if you're talking about this first term here, that is equivalent to this term right here. This 2 is equivalent to this 2. So we have to go from first term to fifth term. That's why. That's all you're doing there in these cases, Brian. That's it. Why am I multiplying the second example, not the first? The first example here was given just as a straight up number. So they just gave us a constant number of 10, and that's it. Okay, so that's all we can do. In this case, it was because of based on the definition we were given here for the sequence. The sequence here was given to us as 5i. So it's like, okay, well, that's our sequence. Let's find each term of the sequence starting from the first term all the way up to the fifth term. And then that's basically what we did. But we're not doing anything too special there, Fritz. So that's why we're multiplying, because of the definition. I'll show off another problem, though, to hopefully clear up any confusion that there may be. All right, so this one here, again, a little bit more complex, but okay, let's look at this one here. I equals 0 to 4 of -1 to the I power over I factorial. Okay, so we're going to find the term of each one here, depending on what I is equal to. In this case, we're going to go from 0 to 4. Okay, so again, the first term in the sequence here is we're going to plug in 0 in for I. We get -1 to the 0 power over 0 factorial. That would be when I is equal to 0. Okay. Again, if you need to, this is where I equals 0. Plus -1 to the first over 1 factorial. This is where I equals 1. Plus -1 squared over 2 factorial, where I equals 2. We're going to go all the way up to I equals 4. So again, there may be 5 of these guys. That's what it is. Okay, so I equals this for 3. And then finally for 4, we have -1 to the 4th over 4 factorial. This is where I equals 4. All right. And we're going to figure each one of these out here and then add up the results together. That's all we're going to do. So what do we get here? -1 to 0 is, oh, that's a good question. What is, let's go over these two parts here really quick. -1 to the 0 power, what's that equal to, ladies and gentlemen? What is -1 to the 0 power? What's that again? You guys tell me. All right. Good you didn't fall for the trap. That is going to be 1. That is correct. Good. What's 0 factorial? What's 0 factorial going to be? All right. Very good. That is correct. If you take a look off to the left here, 0 factorial is indeed equal to 1. All right, so remember, anything to the 0 power is 1. 0 factorial is also equal to 1. Very nice. Everybody's correct. All right, -1 to the first power is -1. That part's true. Over 1. That's fine. We're going to simplify these here, by the way. I'm not going to do it right now, though. 2 factorial is 2 times 1, which is 2. -1 to the third power is -1. 3 factorial is 3 times 2 times 1, which is 6. And then here we get -1 to the fourth is +1. 4 factorial 4 times 3, which is 12 times 2, which is 24 times 1, which is 24. Okay. So, all right. So let's clean this up a bit. Let's see what we get. So we get 1. We get plus -1 plus 1/2 plus -1/6 and plus 1/24. Okay. So let's see what happens here. Super convenient here that 1 and -1, they'll cancel each other out, so that's pretty nice. All we got left is the 3 ugly fractions. Again, if you want to enter that into the calculator, you can. What do I get here? I get 12, I get 4, that's 8, that's 9/24. Which I think that reduces down to, what, 3/8? Alright. Yeah, 3/8 is our answer there. Alright. Again, if you're not sure how that works on the calculator, you can always enter that in here. It's actually not too hard. Let's go 1/2 plus -1/6 plus 1/24. Hit the math key, hit the fraction key. There you go. Got it. 3/8. Good beans. My allergies are... gotta be a lot of pollen in the air today. Alright. Okay. Questions? Questions about that? I hope everybody saw what happened there. Again, you just have to look at your starting number, and you just go to your ending number, and then that's all you got to do for these guys. It's pretty much that easy. Isn't there a sigma key on the calculator? Probably. I just never use it. It's usually a heck of a lot easier just to do it by hand, actually, for these guys, because you can write out every term. I never use it on this calculator. I mean, I'm sure if you have an Inspire, you could probably do it, but yeah, I never use Sigma. I just figure it out. It's really not as bad as it may seem. That's all you gotta pretty much do. I know what the question's there for, though, Brian. You're trying to look for the shortcut. Brian's like, what's the shortcut? Okay, tell it to me. I'd be like, I never use it. I'm like, bro, I'm sorry. I don't use it. You want to find out? You can spend like an hour figuring it out. Be my guest. But, you know. Should I scroll left a bit? Yeah. Sure. The only problem I have with the calculator, in all honesty, because if you found it, that's great. The problem that I have with it is that it's not super easy to work with, necessarily. Like, you'll spend more time formatting stuff in the calculator than you will actually be doing actual work and calculations. So you'll spend an hour fooling around and be like, oh, you spent an hour on a problem that you could have probably wrote out in, like, you know, less than 5 minutes. So I'm like, well, is it really worth the time sink? I guess that's the question that I always ask about certain calculator functions. Don't get me wrong, certain things, do require the calculator. I'm not denying that. I'm just saying certain other things probably you could just do boom, boom, boom without necessarily using the calculator. All right, any other questions before I move forward? Yeah, that's the problem. Is that sometimes the calculator is harder to use than it is actually just writing it out. Like that's just how it is. The problem is that you always want to go. Yeah, look, it's good to have shortcuts. Don't get me wrong. We've used shortcuts in this class quite a bit. Okay, it's not like I wouldn't show you shortcuts that weren't viable. Okay, let's yeah, well, let's be honest with ourselves here. Remember that we when we did matrices, we just did it basically using the calculator, whereas I could have shown you the long way, which would have taken me an hour to explain. I'd be like, in that regard, I'd be like, yeah, you know what? It's a lot easier just to kind of go through that process. Fine, But in other cases, I'll be the reason why sometimes when I write it out by hand, I'm like, that's because I feel that that's the easiest way to get to where you want to be. So sometimes I'm showing you this, I'm like, hey, that is the shortcut because that is the easiest way to actually write it out. I'm like, I don't know how much easier I can really make it, but that to me is probably the easiest way. Won't let me look like an eye. Yeah, again, why I say don't sweat the small details there, Brian. Just write it out as it's defined, and you should be good to go. Spend so much time racking your brain over unnecessary things that you lose sight of what you really need to be doing. That's not something you want to do. I know that. All right. Now, let's go over the next one here. What do I want to do next? Um, oh, Einstein level genius. The good old manual way can't be the worst way. All of it. Okay, so the next one here I'm going to have is sometimes we want to go backwards, okay? So let's say they give you a sequence, okay? Let's say they give you a sequence here. Let's say this is what it looks like. So they can say, okay, what about this? 2 plus 2 squared plus 2 to the third plus dot 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 plus 2 to the 11th. Okay, fine. And what they ask you to do is they don't ask you to find the sum of these numbers. Now you could do that here, but that's not the point. The point that they want you to do here in this particular problem, if they give you a sequence, they want you to write it in notation, in sigma notation. Okay, so they want you to write it in summation notation. All right, so how would you write this sequence of numbers in summation notation? So we're going to have our big old sigma guy here. We'll have I is equal to some number, right? And then we'll have the description of that particular sequence. So how would you write? First of all, let's talk about I. From what number to what number would I put I here as? So that's the first thing I want to think about. From what number to what number would I put I here as? Or again, if you can see what the actual generic form of this particular sequence would be, what do you think that would be? You guys can give me either one of those parts. Fine. 2 plus 2 squared plus 2 to the third plus dot 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 plus 2 to the 11th. Okay. We can start off from what number to what number can you see here, by the way? And if you need a little help here, here's a hint. 2 can be written as 2 to the first. That's your hint. That's your hint here. What number for i's do I have? Yes, you do know where it ends. I beg to differ. You do know exactly where it ends. I equals 1. Okay, that's where we're starting from. I equals 1. 1 to what number? You take a look there carefully, Brian. What's the last number you see there? 11. That's correct. So remember, he goes from 2 to the first to 2 to the 11th. All right? If this was ... okay, if I would be like, so I would agree with you, Brian, be like, if this was just ... then I'd be like, okay, now it doesn't end. Okay, it goes on forever. Yes, that is an 11, 2 to the 11th. Now, you can't fault me for that one. Okay, my handwriting may be terrible, but the 11 looks pretty decent. Okay. So what would be my generic pattern here for this set of numbers? So I have I equals 1 to 11. Fine. What's my generic pattern of numbers here? What should I put down at the inside of this summation here? All right. Okay, that's correct. Very good, Nicholas. Very nice. So the answer is 2 to the I power. All right, good. That's right. So you start from 2 to the first, add it to 2 to the second, all the way up to 2 to the 11th. So the generic pattern here for all those 2 is 2 to the I power. The thing that changes is the I. The exponent is the only thing that changes. So 2 is the same thing that's constant in the sequence. The thing that changes is I, like we had here for our previous examples. Okay, that seems fair. All right, let's look at another one. See if you guys can get this one. I'll put down one here. Go from yeah, let's do that one. So about 1 to the 5th. To the 5th. Yeah. Okay. So Joseph, you have to see it as the generic form here, okay? So you have to see what changes and what doesn't change. So 2 to the I, the reason why it's 2 to the I is what didn't change? Well, the 2's didn't change, did they? So the 2 has to be static in our generic pattern. The thing that did change was the exponent itself, which changed from 1, 2, 3, all the way up to 11. Hence why it's 2 to the I power and not the other way around. So again, what you're putting on the inside of the sigma there is the generic pattern that you see there and where you're going to be plugging in your respective I. Okay, so what changes should be static and what does change, you'll need to put an I in that particular place. All right. How about this one here then? Here I got 1 to the 5th plus 2 to the 5th plus 3 to the 5th, all the way up to 20 to the 5th power. What would I have here for my summation notation? I equals 5. I equals 5. I equals 5? Let's try again. Remember, we're talking about i's got to start at some number and end at some number. So where's I starting from and where is I ending? Again, I is the number that constantly changes from term to term. So that just says posture check. Thank you. The answer, I to the fifth. Okay, I can agree with that. I have I to the fifth power. Again, the powers don't change. They're all to the fifth power, right? But the I here is the thing that does change. So where does I start and where does I end? That's what we have to answer here. That's our summation numbers we're going to put there. I is equal to 1 and 20 on top. Okay, that's correct. So I starts at 1, and that changes 1, 2, 3, 4, 5 all the way up to 20. That's correct. Nice. That's how we can write summation notation for that. Easy peasy lemon squeezy. All right. Okay, let's try one more here. Okay. So I'm going to write it this way: 4 plus 4 squared over 2 third, 3 plus dot 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 plus 4 to the n. Okay. Again, a good hint for you here is, again, you can rewrite 4 as 4 to the first over 1. That's fine. Do that. So we want to write that in summation notation here. So let's talk about I or the generic pattern here, whichever one you want to go with. So what would I go with? What would I start with and what would I end with? We talked about, say, I goes from 1 to 20 in the last example. Okay. What about I in this particular example? What would that be? Hmm. Hum. All right, I starts from 1. And what do we go till? So 1 to what? What would be the last number in this sequence? What do you see? Yeah, that's correct. I goes from 1 to n. That's right. Not infinity here. Not infinity. This is a finite sequence. Now they give us, the thing is, it's not infinite because I don't have dot 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 at the end. It's not just trailing off. I have from I equal 1 to n is correct though, because we do stop at some point. They don't tell us what that last number n is. Okay, we have no idea what that number is for n, okay? But we do know it stops at some random point here of n. It could be 500 for all we know, but it doesn't really matter. It says I equals 1 to n, and it stops there. Okay. Now that we have that established, now how would you go ahead and describe your sequence here? How would you describe your sequence? This one's actually a bit easier to generally describe the sequence. A good hint here would be to look at the very last term of this sequence. Don't use ends here, Nicholas. You have the right idea, though. But I do want you to look at that last term there. That's true. But don't use n, because n is a specific number here. There you go. That's correct. All right, good. 4 to the I over I. Yeah, we're going to use I here because that's what we have to use I, right? That's the index we're using here. We're not using n. N is going to be like a specific number that it ends off at. Okay, but I here is the one that constantly changes, all right? So that's why we're having 4 to the I over I here as the generic description of our sequence here. Okay. All right. Yeah, good. Everybody's got that down. Any questions about that? Any questions? Okay, good beans. All right, so that is we're almost done with this section, but there are properties that go with summations. We're not going to really discuss about it too much, but you can split up summations, or you have constants here. So I do have this up here. It says, how do we solve summations and what are some properties? We talked about how to solve for summations here already, but some properties here that you can see is if you have a constant number here, you can go ahead and take that constant and bring it out to the front if you want to. If you're adding two sequences together here, you could split that apart into their own separate summations. And this last one here, again, if you're subtracting, then you can split it up into your two separate summations. That does not obviously apply to multiplication division. Those are its own. That you have to look at case by case. Does number 5 on the worksheet transition number 5? Number 5 is still part of 8.1. Number 6 is the beginning of 8.5. Hey, Goldmish. Yeah, just to clarify, these are just some extra bits and bobs about properties of summations. I'm not going to talk about it like a lot, but again, it's there. I just wanted you to see the patterns and stuff, so you guys can see that for yourself. So that shouldn't be overtly too hard. All right. Let's take a good look here at the next one here. Let's go to section 8.5. If anybody has any other questions, just let me know. Section 8.5 talks about the binomial theorem. Okay. So exactly how does the binomial theorem work? Well, in a sense, what we're going to be doing is we're going to be, let's say you're adding two things together, okay? Regardless of whatever those things are. It could be a plus b, and let's say you had like a plus b to the 22nd power. Now, and they ask you, hey, can you tell me what the what a plus b to the 22nd power would be if we were to write it all the way out? Now, obviously, multiplying a plus b to like the 22nd power is absolutely bananas, okay? There's just a lot going on in that particular problem. But what if there was a way we could go ahead and shortcut our way to get to the answer here without having to write out all the work? Well, that is certainly plausible. We don't have to multiply a bazillion times. There is a definitive pattern behind how you can find out something like that, hence why you have the binomial distribution of binomial theorem here that you can use in order to find out the answers to those problems. So what we have in those cases is we have what's called a binomial coefficient. Let's take a look at that here and how it works. But I do want to talk about its notation here and how it's actually said. Here we have this these parentheses here with an n on top and an r on the bottom. Now it does have a definition here, and this is equal to n factorial over r factorial times n minus r factorial. This is incredibly important. This is actually one of the most important concepts here, not in this section, but in practicality purposes. This formula here is used a lot. In real life applications, if you say, where's this useful in real life? This is actually useful in real life, this particular formula, for sure. Now, the way we actually say this is we use n choose. The way we want to say this, I often say it, is n choose r. Okay? That's how we're going to actually state this, n choose r. By the way, if you want to know why this is super useful, is because if we're talking about statistics, this is the formula here for the number of combinations of something. So if you ever wanted to figure out your odds of, say, like winning the Powerball, the way to do that in that case is actually to use this particular formula here, and you can actually figure it out. Ever wonder how they come up with the number? Well, this is how they use it. This is how you can find it. And even if you tweak the rules, you can use this same formula. You can find your new odds of winning. Same deal. And then you just got to multiply by how many Powerballs you got. And then that's pretty much it. So we get, what, 292 million? Yeah. Again, that's the... But that's how you get, like, 1 out of 292 point blah, blah, blah million. Like, how do you come up with that random number? Like, how does it even happen? Well, there you go. That's how it works. All right. Okay. Now, the way we could go ahead and figure this out here, I do want to point one thing out here. Although I do say n choose r here, I also want to point out one more thing here, and that is the calculator. You can figure out the calculator here as well. There is a calculator function. That is this function right here. Calculator is NCR. Make sure you have that in your notes here. We will be using that here in this case because one of the things is that this takes a long time to kind of do by hand. N factorial over r factorial, especially if you have multiple of them. They can be a little cumbersome to do. So there is a calculator function here, which I will show you here in just a moment. All right. Before I move on, any questions so far? Okay, let's do an example. All right, now one thing that you will never have is n is always going to be the largest possible number. So you're never going to get like 3 and 4 here. You're never going to get 3 choose 4. That doesn't make any sense. Okay, so that'll never happen. We don't deal with negative numbers in factorials, so that's fine. So let's say we have 6 choose 2. Okay, so this is how I'm going to say it. I'm going to say, let's say we have 6 choose 2. Again, as a practical formula, you can enter that in. That's 6 factorial divided by 2 factorial, 6 minus 2 factorial. So again, you have 6 factorial, no, that on the next line, actually. 6 factorial over 2 factorial, 4 factorial. Now, like I said, you can enter this into the calculator if you like as manual like this, but again, you do want to take a shortcut in this case. So let's show practically how we can do 6 choose 2. So the way you want to do 6 choose 2 on a calculator, depending on what version of TI that you got, it can look at one of two ways. But you're going to do the same button presses regardless. So the first thing that you're going to do here is you're going to hit the number 6. So go ahead and hit the number 6, all right, on your main screen here. And then I want you to go ahead and hit the math key. So if you hit the math key here, all right, and if you go back to our PROB menu, where we found our factorial key, right above the factorial is the NCR key. So that's choice number 3 here, which says NCR. And we're going to go ahead and hit enter here. Now, if you have a newer calculator like what I have here on my screen, of course this is like the PC version of the calculator, then it's going to format it for you anyway. All right. If you have the old school calculator, it's going to look like this. It'll be 6 NCR, and then you put the 2 after that. So it'll actually just write out the actual NCR, just like right next to it. So it just depends if you have the new school or old school calculator, if it'll do the formatting for you or not. If it does the formatting, just enter in 2, and just hit enter after that. So here we get 15. So I just wanted to point that out there, be like, oh, okay, you know, where the heck you come up with that stuff? Okay, well, yeah, we actually, you know, there you go. Let's do another here. I do want to showcase one more here. It is possible to have 0, by the way, so you could have, say, 5 choose 0. So 5 choose 0 is actually, you don't even need a calculator for this one because of what happens. So 5 choose 0 is 5 factorial over 5 minus 0 factorial. We know by default here 0 factorial is 1. Oops. Should be on the outside, not on the inside. Alright, in any case, we're going to have 5 factorial divided by 1. 5 minus 0 is 5, so we're going to another 5 factorial. 5 factorials essentially cancel out. That just leaves, that's just 1 divided by 1, which is, so, there you go. So you don't do anything with the 4. No, if you want to do it like the manual way, you can have 2 factorial divided by 4 factorial. Like, it does factor into the answer if you're talking about the previous example there, Brian. Like, if you're doing it the manual way like we did in the last section, then yeah, the 4 obviously factors into the answer, but it's gonna do it in your stead if you do 6 choose 2. Yeah, so it'll do that again. This NCR, that's a set formula in the calculator, Brian. That's a set formula. Okay, so it's gonna do that for you already. All right. Number of combinations is exactly n factorial over r factorial n minus r factorial. So you could take that to the bank and then some. Always. Like I said, I'll show you a shortcut when I feel it would be necessary. This is definitely where it would be necessary. So, all right. Okay. So you're probably wondering, where is this going to be helpful? All right, let's take a good look here at the binomial theorem. And then we'll take a look at actually both of these questions here. So we need to actually acknowledge both of them here. So what is the binomial theorem? The binomial theorem works like this. You have a plus b to some power n. All right? And so that's going to equal, we have a pretty distinct pattern here. We have n choose 0. Oh, this needs to be modified here, which I will in just a second. N choose 0 times a to the n plus n choose 1 times a to the n minus 1 times b plus n choose 2 a to the n minus 2 times b squared plus n choose 3 a to the n minus 3 b to the third, all the way down to b to the n power with n choose n. Essentially, every term you go down, you're subtracting 1, you're adding 1 to the n choose r here, and then you're also going ahead and subtracting down a power from n and adding 1 power to b. That's essentially how it works here for this particular guy. Now, let me modify this a bit because this generic pattern is actually wrong. I forgot the n choose part here, so I'm going to put that in right now. Because what needs to happen here in this sequence specifically is I need this. So, a little behind the scenes work here, but nothing that can't be corrected. There we go. That's how it's going to work. Perfect. I meant to put that in and I totally forgot that. All right. Okay. Ah, no. Holy smokes. It's too big. There we go. All right. Sorry, there should be an n choose r there because we need to go that every time down. Okay. Okay. So how do we find a particular... Now, based on this formula here, this is basically what we want to be doing here. How do we find a particular term in a binomial expansion? If you want to find the r plus first term in the any binomial expansion, that's going to be n choose r, a to the n minus r, b to the r power. Okay. Again, I want you to also note in a binomial expansion, you always start from 0. You do not start from 1. Okay, you start from r is equal to 0 and not r is equal to 1. So please be very careful about that. Okay. All right, so actually I'll put that as a note here. Note, you always start from r is equal to 0. Okay. I'll put that as another note here, so to give you a reminder of that. And the reason, the specific reason why I actually state that here is because some problems will ask you to find like the first few terms, and you need to know that you're starting from r is equal to 0. You're not actually starting from r is equal to 1. So a common trap you can find yourself in. All right, let's look at some sample problems though, because we're going to actually practically put this together, and then we'll see what we're going to get. So let's start off with something nice and easy, and then we'll work our way up. So let's say we have x plus 4 to the 4th power. Okay, so let's say this is what we want to expand. I'm going to take this binomial, I'm going to take it to the 4th power, and without multiplying everything out, I'm going to go ahead and write out exactly what this is going to equal to. Okay, that's what I want to do. All right. So if I expanded it out without having to do like, oh, this times this and foiling and all that stuff, forget all that. We want to use this formula here, number 7, this binomial theorem. We actually want to figure out all the coefficients, all the powers, and how does that all work. So the way this works, let's go down the line here. Let's go down the line. The first thing that I want you to identify here, and what is important, is in the generic formula we have this a and b. This is going to prove to be fairly important because a here is going to be x and b here is going to be 4. Do not forget this. This is very important. Okay. N here, on the other hand, will be this 4 right here. All right. Keep this in mind. Label each one of your parts here if you're going to expand this out, because you're going to need it, every single one, in order to make this work. So the way it works is, let's start off by using the formula here. The formula here says n choose 0. Well, our n here is 4, so we go 4 choose 0. It says a to the n. A is x. Okay? So we have x here. I'm going to put this in parentheses here for a reason. But this is x to the 4th power. Okay, that's our n. Going to add to that here. Now we go 4. This gets bumped up by 1. So this bottom number here, which would be the r, this gets bumped up by 1. And here we take x, we'll put that x. That gets bumped down by 1 degree. That gets bumped down by 1. That's 3. And then we now have 4. And 4 gets put up by 1. In this case here, if this highlights it as well, this would be like, I'm just going to write this in temporarily. This would be like, I don't want, so like in here, there would be like 4 to the 0 power, which is 1. But again, you don't have any 4s to start with in that first term. I just wrote that in kind of as a temporary thing, but I'm just going to erase it out. So now we just add a 4. Now we have 1 4, essentially. All right. This goes up to 4, choose 2. We bump down one of the x's by 1. We have 1 less x. And we have 1 more y. 1 more b. Y or whatever. Or things. All right. Let's put it here on this next line. All right. Plus 4, choose 3. So we're going to bump that up by 1. That guy. We'll take down 1 x. Okay, so we have 1 less x than we had from before. But now we have 1 more 4 we had from before. We have 4 to the 3rd. Now we have, finally, we have 4 and 4. We bump that up by 1. We have 1 less x, so we have no more x's. And we have 4, bump up the 4 here by 1. Or we get 4 here. Okay. All right. Any questions so far? Let's stop right there for just a second. Oh, okay. All right, now we want to figure out each individual part. Again, if you want to, you can use the calculator to figure out 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. Let's go ahead and figure out a couple of them. So I get 4, math, go to number 3, NCR. So we're going to do 4, choose 0. That's 1. So here we get 1 times x to the 4th. So we get 1 times x to the 4th. I'll just put the 1 there. 4, choose 1, if you do that out here really quick. 4, choose 1 is going to be 4. Okay. Gotta know this by default here, but we get 4. Here we get x to the 3rd. And then here we get times another 4. Again, that's from 4 to the 1st here, by the way. All right. Next we get 4, choose 2. So if we put in 4, choose 2 here, we get 6 times x squared times 16. We do 4, choose 3. 4, choose 3 should also be 4. And so we get 1x left over, and we get 4 to the 3rd, which is going to be 64. Finally, we get 4, choose 4, and if you do 4, choose 4 out, I know I'm kind of taking shortcuts here. 4, choose 4. Math, PRB, CR4. That'll be 1. We have 4 to the 4th here. which is going to be 256. So. Alright, and now we just want to simplify stuff down. So let's see what we get here. So our final result here is x to the fourth plus 16x to the third plus, was that the 96x squared plus 256x plus 256. Alright. Alright. Actually, yeah, that's right. Never mind. Okay, now I got that. Okay, and that's it. That's how you can expand that out without too much trouble. Question mark. Questions, questions, questions. I'm gonna do another one, but any questions about that? Hopefully that was easy. Hopefully that wasn't as bad as you thought it was. Stretch out here. Alright, let's do another one. I have to do this next one because this one's actually pretty important. So. Okay. Let's say I had to expand this out. 2x minus 3 to the fifth power. Okay, and I wanted to expand this all the way out to its respective things. Now, one thing that I will tell you here is, like, how does it work here with, like, negative numbers? Again, one of the things that'll be especially important in an example like this is just to rewrite the problem here to put it in the correct context of what you're going to be doing. Again, minus 3 here, you can write it as 2x plus negative 3 to the fifth. Now you'd be like, well, why would you do that? That seems a little silly. I'd be like, well, again, you need to know what numbers you need to put in specific places. So again, a would be 2x, okay, b would be negative 3, and n here would be 5 as a result, okay? So now I want to apply the formula here once again in the same exact manner that I had from before if I'm going to write that whole thing out. Now you'll see how this will work, at least in this instance. This is going to work a little different than what you think, but notice that I put, if you looked at the last example, I put parentheses around stuff here. Again, that was purely on purpose here, okay? So, and for problems that look like this, as complicated as they look, they're not as bad as it may seem, okay, once you understand why those parentheses go there. For example, in this case, we would have a to the fifth power, or a to the n, or a to the fifth. That a is 2x, which is specifically in parentheses, and you take that to the fifth power, because that's what a is equal to, okay? We have 5 2x's to start with, okay? And we're going to figure that out at the end of the problem, but that's essentially what we're working with. Here you have 5 choose 1, and here you have 4 2x's left, and you now have 1 negative 3. Okay. Keep going down the line here. 5, choose 2. We have 3 2x's left over. And we have 2 negative 3's. So here we have 5, choose 3. We have 2 2x's, and we now have 3 negative 3's. Here we have 5, choose 4. We have 1 2x and 4 negative 3's. And then finally, the last one here, until we actually put everything together, we have 5, choose 5. We have no 2x's here, so that's been gone. And we have all 5 negative 3's. Okay. We get the 5 cents. I got our garbage, I'd let you know. Alright. Okay. So if we put this together here specifically, now we go ahead and put this together here. Now 5, choose 0, again, you can figure that on the calculator, that's going to be 1. 5, choose 0, 2 to the 5th is going to be 32. We get 32x to the 5th. Gonna have to go through this pretty fast. 5, choose 1 is 5. We get 2x to the 4th, so that's 16x to the 4th. Times negative 3. Alright, 5, choose 2 is going to be 5, 4... That's 5 times 4 over 2, so that's going to be 10. Again, you can use your calculator to verify that. Most of this stuff you can use your calculator to verify, so I'm just doing this in my head. So 2x to the third is 8x to the third, and then here we get 9 because negative 3 squared, so positive 9. Let's do the next one here. We're going to add 5, choose 3, which is also 10. You get 2x squared, which is going to be 4x squared. Negative 3 to the third is negative 27. 5, choose 4 is 5. Here we get a 2x, so that's fine. Negative 3 to the 4th is going to be 81. Positive 81, that is. So there we go. And then here we get 1. 5, choose 5. And negative 3 to the 5th here is negative 243. Now we're going to add this all together. We're going to come up with a grand final answer here. So let's see what we get. Alright, so here we get 32x to the 5th. Okay. 5 times 16 is going to be 80. Times negative 3 is minus 240. X to the 4th. 10, 80, 720. 720 x to the 3rd. Let's see here. That's going to be 227 times 4, which is going to be, that's 8, that's 108, right? So minus 1080 x squared. All right. Let's see, what do we get here? 10, 810, so plus 810x. Minus 243. Alright, so that's our final answer for this problem here. 32x to the 5th minus 240x to the 4th plus 720x to the 3rd minus 1080x squared plus 810x minus 243. There we go. Got it, put it all together. Yeah. Mental maths. Again, you can use a calculator to figure out that stuff there, but I just used my head for that one. There you go. Alright. Any questions about that? Notice what I put in parentheses. Again, you may have to do a little bit of that little side scratch work there at the end. You could have 2 letters there if you need to, but okay. I know you don't have questions, Cool Mash. Yeah, I can do that. Sorry, the paint tool doesn't do great justice, but there you go. No problem. Okay. Now I do have one more example to do. The reason is this is actually a rather important example. So, as well, because you'll get this problem here in this section as well. So I just need to showcase this off. I got like 5 minutes, but it will take less than 5 minutes to explain. So, all right. Let me quickly do this last example here, and then we're done with these two sections. So, okay. So the last example here talks about finding a particular term in a sequence. So our example here, this is going to be part of question 8. Yes, that is correct, Joseph. So some questions are going to ask you, hey, find me this specific term in this sequence if we were to multiply everything out. So let's say, for example here, they ask us, hey, can you find the, let's go with this one here. Find the third term. Find the third term in the sequence here. Let's say, I'm going to go ahead and borrow this here. 2x plus y, 2x plus y. Come on, brain. Brain, use your brain. 2x plus y to the 6th power. Let's say find the third term in that sequence, okay? That's what we want to find, all right? So, tell me exactly what that term would be. That's basically what they're asking you to do. Now, the real question is, how do we find that term? Now, that's what number 8 is going to reflect. If we want to find the r plus first term, then we have to use this formula here, n choose r, a to the n minus r, b to the r. Now, the one thing I want you to clue in on here, very carefully, this is where you need to be very extra careful, is that on the left-hand side, that says r plus first term, right? The first term in the sequence, if you take a look at the binomial theorem regular formula, has basically this guy here, this r equal to 0 to start with. This is your first term right here, is when r is equal to 0. This is incredibly important. This is why it says the r plus first term here. R would actually be 0, and that would reflect your first term. If I want to find the third term in the sequence, I need to define what r is. In order to do that, set r plus 1 equal to 3, okay? So this r plus 1 is going to factor into how we're going to actually approach this problem. This r plus 1 is going to equal to 3, and in reality, you're not using 3 for r. In reality, you're using 2 for r instead. Okay, so what I like to do is I like to give people this reminder here is like, I don't need to use 3 actually for r here. I'm actually using 2 here for r instead, okay, to get that next term going. So if I were to write this out using our formula, I'm going to have n, which is 6 in this case. That's what this n, we have 2x plus y here. Again, you can label your a and b here respectively. We have 6 choose 2. And then we have a, which is 2x. We have 6 of them. We're subtracting 2 of those a's out. And we're keeping, we have how many y's? We have 2 y's. Again, that r plays a very big role here in this particular question, okay? And now we just got to put the pieces together here, and so we see what we get. So let's put it on the calculator here really quick. We got 6 choose 2, so 6 math. Let's go to choose here. So we get 15 for that. Let's clean this up a little bit. We get 2x to the 4th. We'll clean that up in a second. And we got y squared. All right. So putting this together here, we need to clean it up a little bit more because we need to figure out 2x to the 4th. And 2x to the 4th here is going to be 16x to the 4th. and you get y squared. And so if you do 15 times 16 here, we get 240 x to the fourth y squared. So this is specifically going to be the third term in our sequence of 2x plus y to the sixth power. Okay? So again, the key part here is actually here at the very beginning of the problem in defining what r is. Set that r plus 1 equal to that particular term number you want, and then use that r in your generic formula that you have here in number 8, defining whatever a, b, and n is going to be, and then there you go. Is it always going to be r plus 1 is equal to 3? Again, the reason why I use 3 there, specifically, Joseph, is because we wanted to find the third term here. This could literally be anything. So if you said find the fourth term, I would set r plus 1 equal to 4. The r plus 1 stays the same all the time. It's the term though that's different. So because they could ask you for literally any term in the sequence. So any other questions about that? Any questions at all, ladies and gentlemen? All right. Very good. Very good. Okay, so that's where we're going to end off here for today. That, in effect, is the end of Chapter 8. Alright, that was all of Chapter 8 that we did in a single day. So, that, in effect, just to let you know, is the end of any of the new material that we're actually going to have in this course. Okay, so that is effectively the end of the textbook here. Everything is done and dusted. All right. So as I said earlier here today, that means that for the next couple of weeks here, we're going to be going over review here. Any questions that you may have over homework and the like, you guys can bring that to me here starting on Monday, and we can go over anything that you would like me to talk about. Okay? Or if you just want to shoot the breeze, I got no problems doing that too. But again, homework questions and whatnot should come first. So if you say, hey, Professor Chips, I need you to do like, can you show me how to do like number 5 from section, 3 point whatever, then fine. We could take a look at that and see what's going on with it. So, I have no problem with that whatsoever. All right. Joseph says the hydrate. Thank you. All right. No problem, Lysander. I really appreciate it. Thank you. Thank you for coming on out. That's all that matters. I'm just glad again you're making an investment into yourself. So, all right. At the end of the day, anyway, everybody, please enjoy your weekend. Again, everything is posted. It's ready to go. Thank you so very much, everybody. You guys are absolutely wonderfully fantastic people. I love all of you. You all are absolutely great. Thank you for making this class enjoyable and fun. And we'll be having fun here for the next couple of weeks still. So we'll still be here online. We'll still be doing the live streams, no question. Same time, same place, everybody. Have a great rest of your day, afternoon, evening, whatever. And have a great weekend as well. You guys know exactly where to find me. I'm on Discord. Contact me via email. Whichever way you want to do it, I don't mind. All right. In any case, everybody, have yourself, again, a great weekend. Take care of yourselves, everybody. And as always, everybody, stay safe, stay healthy, but most importantly, stay sane. Have a great one, everybody. Take care. We'll see you on Monday. All right. See you later, everybody. Bye. Bye, everybody.